In this video, we are going to review how to use the patterns in a 30, 60, 90 degree triangle to find the missing sides of all 30, 60, 90 triangles. So first thing I'm going to do is look at just the structure of this triangle and think about what I know to be true. I have my 60 degrees here, 30 degrees here, and a right angle here, so that is 90. One thing that I could do here is if I were to reflect the triangle over this height here, I would see that that angle would now be 30 and this angle would be 60 because it's reflecting across. And from that, I would be able to tell that I have a 60, 60, 60 triangle, which would make this a equilateral, where all sides and all angles are equal. I can use that knowledge here to say like all of these sides would be equal to 2 because they are all equal and all of the angles equal 60 degrees. Well, if I go back to my original triangle, this triangle in black, I will see that this side is 2. And if this whole thing is 2, that means that this piece just right here is equal to 1 because this is exactly half of this triangle. So that's how I can find at least 2 of these values. Now if I want to find this third value, let's say I want to find the height here in green, I could use the Pythagorean theorem. I could use this because I have 2 sides of a right triangle and I want to find the third missing side. So I can call this A, B, and C. Substitute my values. And I end up getting that B is equal to the square root of 3. I'm going to leave everything in exact form for this. So instead of B now, I have the square root of 3. And we can use this original reference triangle here to actually find any missing side that has a 30, 60 degree, a 30, a 60, and a 90 degree angles in a triangle, because I know that all other 30, 60, 90 triangles will be similar from this, and so they must have the same scale factor. That means that any other 30, 60, 90 degree triangle would have the same scale factor from these. They would all be multiplied by the same number because the 60 degrees and the 30 degrees prove that these two triangles, well, those two triangles would be similar. So let's see how we can actually use that. Let's find the missing side lengths and leave our answers in exact form. That means with our radical symbol here. We're not going to use a calculator. So, like I was saying, I see that this is 30 and 60 degrees, which means that it is similar to our original triangle. This pattern of numbers here is what we will use to find our missing sides. So my original was 1, 2, and the square root of 3. And I have this new triangle that has 8, x, and y. Now, I know that these are similar triangles, which means that their corresponding sides are proportional. So like this side for the 2 and this side for the 8, those are corresponding sides. This side for x and this side for the square root of 3 are corresponding sides. And this side 1 and this side y are corresponding sides. So if I want to find x, I want to find this missing side of x, I can set up a proportion with the 2 sides that I do know and the corresponding sides that include the value I'm trying to find. The next thing I would do would be to multiply across. And I get 2x is equal to 8 times the square root of 3. I'm going to divide both sides by 2. I get x equals 8 and 2 can be simplified. They can both be divided by 2. So I get 4 square roots of 3 over 1, which I do not need to write here. So that means that the x is equal to 4 square roots of 3. And now let's use the same idea to find y. So go ahead and pause the video and see if you can set up the proportion to find the missing side y. So I'm going to set up the 2 corresponding sides that I do know, and then the corresponding sides that include the value I'm trying to find. I'm going to multiply across, and I get 2y equals 8. Divide by 2 on both sides, and I get y equals 4. Now, this makes sense. If we're looking at our original triangle here, there's always going to be a relationship from this short leg to the hypotenuse that's times 2. And there's always going to be a relationship between the short leg and the long leg that's going to be times the square root of 3. So if I look back here, I see from 4 to 8 was times 2. And from the short leg to the long leg, it was 4 times the square root of 3. So that pattern is always going to hold true, and I can think about these being halves and this being times the root of 3. I can always come back also and use my similar proportions here to find what that value would be. So let's see another example here. Go ahead and pause the video and see if you can figure out how to start this problem or how to set up the proportions. So the first thing I'm going to do is sketch out my reference, which I know is 1, 2, and the square root of 3. So I'm writing that there. I'm also going to rotate this so it's in the same orientation as my reference triangle. It just makes it easier for me to see. And then that square root of 5 is the hypotenuse here. All right, and I want to find x and y. So I'm going to set up my proportion to find x. I'm writing the 2 sides that I do have values for, or 2 corresponding sides that I do have values for. And I'm going to put that over the corresponding sides for the value I'm trying to find. Then I'm going to multiply across, and I get 2x equals 5 square root of 5 times the square root of 3, which I can rewrite as 2x equals the square root of 15. I can then divide by 2, and I'm left with x equals the square root of 15 divided by 2. And go ahead and put that here. And then I'm going to go ahead and find y. Set up my proportions for the sides that I do know are true. Multiply across. And simplify. And I get y is equal to the square root of 5 over 2. And let's think back to the pattern that we saw in the original, where the short leg to the hypotenuse is times 2. But if I'm looking at it from the hypotenuse to the short leg, it's divide by 2. I can see that is true here. The hypotenuse is the square root of 5. So I know if I'm going to divide by 2, well, that's the square root of 5 over 2. So that checks out. I also know that from the short leg to the long leg is multiplied by the square root of 3. So if I look at that here, that's exactly what happened. We multiplied the short leg, which is the square root of 5 over 2, by the square root of 3. And square root of 5 times square root of 3 is that 15 right there over 2. So that checks out as well.